Welcome! In this session, we'll tackle problem number 141, linked list cycle. This problem is a classic example of how to detect cycles in a linked list, a common data structure interview question. We'll explore different approaches, analyze their efficiency, and understand when to use them. Let's dive in. In this problem, we are tasked with determining whether a given singly linked list contains a cycle. A cycle exists if, by repeatedly following the next pointers, we eventually arrive back at an earlier node in the list. The parameter POS is used internally to indicate the index of the node where the cycle begins, if one exists, but it is not provided as an input to our function. Instead, our goal is to simply return true if there is a cycle and false if there isn't. The input to the problem is the head of the linked list, which is a list node, and the output is a Boolean value indicating whether a cycle is present. Now let's look at an example to understand this problem better. Here, the input linked list has nodes with values 3, 2, 0, -4, and the parameter POS is 1. This means that the next pointer of the last node, which has a value of -4, points back to the node at index 1, which has a value of 2. As a result, the list forms a cycle. The visualization shows how the pointer from -4 loops back to 2, creating the cycle. In this case, since a cycle exists, the output is true. In another example, the input linked list has nodes 1, 2, and POS is 0. This indicates that the next pointer of the last node, which has a value of 2, points back to the first node, which has a value of 1. The visualization illustrates this cycle, where 2 loops back to 1. Since there is a cycle in the list, the output is true. Let's consider a different scenario where the input linked list has only one node with the value 1, and POS is -1. Here, POS equals -1 signifies that the node does not point back to itself or any other node, meaning there is no cycle. The visualization shows a single node without any back references. As there's no cycle in this case, the output is false. Now, let's cover the constraints and edge cases for this problem. The linked list can have between 0 and 10⁻⁴ nodes, and the value of each node lies between -10⁻⁵ and 10⁻⁵. The parameter POS is either -1, indicating no cycle, or a valid index in the list. For edge cases, if the list is empty, meaning head is null, there cannot be a cycle, so the output is false. Similarly, a single node with POS equals -1 also has no cycle. However, if a single node points to itself, forming a cycle, the output is true. These constraints and edge cases help us understand the problem's boundaries and special scenarios. Additionally, for a large list with many nodes but no back reference, where POS equals -1, the output should always be false regardless of the size of the list. For example, a list containing values from 1 to 10⁻⁴ without any cycle will return false. These examples and edge cases highlight the key situations we need to handle when solving the problem and ensure our solution works for both simple and complex inputs. To detect a cycle in a linked list, the brute force approach involves using a hash set to track visited nodes. The idea is simple: as we traverse the list, we store each node in the hash set. If we encounter a node that's already in the hash set, it means we've found a cycle. This approach works by starting at the head of the list and iterating through each node. At every step, we check if the current node is in the hash set. If it is, we return true because a cycle exists. If it's not, we add the node to the hash set and continue. If we reach the end of the list without finding any repeated nodes, we can conclude there is no cycle. While this method is conceptually straightforward and easy to implement, it does require extra memory to store the hash set, making it less ideal for environments where memory is limited. The time complexity is O(n), since we visit each node once, but the space complexity is also O(n), due to the memory needed for the hash set. An optimized approach to solve this problem is Floyd's tortoise and hare algorithm, which uses 2 pointers moving at different speeds to detect a cycle. The key idea is that if a cycle exists, the faster pointer, called the hare, will eventually catch up to the slower pointer, called the tortoise, as they move through the list. In this method, the slow pointer moves 1 step at a time, while the fast pointer moves 2 steps. If there is no cycle, the fast pointer will eventually reach the end of the list, confirming that the list is acyclic. However, if there is a cycle, the fast pointer will lap the slow pointer, and they will meet somewhere within the cycle. To implement this, we initialize both pointers at the head of the list. In each iteration, we move the slow pointer one step and the fast pointer two steps, then check two conditions. If the fast pointer or its next node becomes null, the list is acyclic. If the slow pointer equals the fast pointer, we've detected a cycle. Floyd's algorithm is highly efficient, with a time complexity of O(n). This is because the fast pointer traverses the list at most twice, and there are no additional operations beyond the traversal. The space complexity is O(1), as no extra data structures are used, making it extremely space efficient. Compared to the hash set approach, this method eliminates the need for additional memory, which is a significant advantage. However, it's worth noting that Floyd's algorithm can be slightly more challenging to understand and implement, as it involves managing two pointers and their movement logic. Another alternative approach is to mark visited nodes by directly modifying the list, for example, by changing the value of nodes to indicate they've been visited. While this method is also space efficient with O(1) space complexity, it alters the input list, which is often not permissible in many problems. Therefore, despite its simplicity, this method is generally less desirable for practical use cases. The most suitable strategy for this problem is Floyd's tortoise and hare algorithm. It strikes the best balance between efficiency and practicality, achieving O(n) time complexity and O(1) space complexity. While the hash set approach is easier to implement, it requires O(n) additional memory, which can be a limitation for larger datasets. On the other hand, modifying the list to mark visited nodes is space efficient but alters the input, which is not acceptable for many scenarios. The key insight behind choosing Floyd's algorithm is the realization that two pointers moving at different speeds will either meet in a cycle or terminate in a non-cyclic list. This method respects the integrity of the input list, avoids extra memory usage, and is highly efficient, making it the optimal choice for solving this problem. Although it's slightly harder to implement than the hash set method, the trade-off in space efficiency more than compensates for the additional complexity in coding. The problem we are solving is to detect whether a singly linked list contains a cycle. A cycle in a linked list occurs when a node's next pointer points back to a previous node, creating a loop. To solve this, one straightforward method is the brute force approach, which uses a hash set to track visited nodes. The intuition here is simple. As we traverse the linked list, we check if the current node has already been visited. If it has, then a cycle exists, and we return true. Otherwise, we add the node to the hash set and continue. To begin, we initialize an empty hash set to store references to visited nodes, and we start the traversal from the head of the list. During the traversal, for each node, we check if it exists in the hash set. If it does, we know there's a cycle and return true. If it doesn't, we add the node to the hash set and move forward. After adding the current node to the hash set, we move to the next node in the list and continue the process. The traversal ends when we reach a null pointer, which indicates the end of the list. If this happens, it means no cycle exists, and we return false. It is also important to consider edge cases. For an empty list where the head is null, we can directly return false because there are no nodes to form a cycle. Similarly, if the list contains only a single node without a next pointer, it is impossible for a cycle to exist, so we return false. These checks ensure that the algorithm handles all possible scenarios robustly. The key insight behind using a hash set is its efficiency. A hash set supports average O(1) time complexity for both insertion and lookup operations, making it an ideal choice for tracking visited nodes during the traversal. By leveraging this data structure, we can quickly detect cycles without revisiting nodes unnecessarily. The hash set approach also allows us to achieve a linear time complexity of O(n). This is because we only traverse the list once, and each node is either added to the hash set or checked for membership, both of which are constant time operations. However, this efficiency comes at the cost of additional memory usage. Since the hash set stores references to all visited nodes, the space complexity is O(n) in the worst case, where there is no cycle and all nodes are stored. To summarize the edge case handling, if the list is empty, we return false. If it has only one node without a cycle, the algorithm recognizes this and returns false after completing the traversal. If a cycle starts immediately, such as when the first node points to itself, the algorithm detects the revisit during the first iteration and returns true. This ensures that the solution is both comprehensive and efficient. The algorithm is also equipped to handle large linked lists effectively. Even for longer lists, the O(n) time complexity ensures that the solution remains scalable, as we only pass through each node once. To see this approach in action, let's examine the pseudocode. First, we define a function has_cycle that takes the head of the linked list as input. Inside the function, we create an empty hash set called visited and initialize a pointer, current, to the head of the list. As we traverse the list, we use a while loop to check each node. If the current node is found in the visited set, we return true to indicate a cycle. Otherwise, we add the current node to the set and move to the next node. If the loop ends without finding a cycle, we return false. This concise implementation highlights the simplicity and effectiveness of the hash set approach for detecting cycles. Now, let's analyze the complexity of this algorithm. The time complexity is O(n), because we traverse the list only once, performing constant time operations for each node. The space complexity is O(n) in the worst case, as the hash set stores references to all unique nodes in the list when there is no cycle. While the hash set method is straightforward and intuitive, it does require additional memory to maintain the set of visited nodes. As an alternative, we can consider Floyd's cycle detection algorithm, also known as the two-pointer approach. This method uses two pointers, a slow pointer and a fast pointer, to detect cycles in O(1) space. However, for clarity and simplicity, the focus here remains on the hash set method. This approach provides a solid balance of efficiency and ease of understanding, making it a reliable solution for detecting cycles in singly linked lists. This implementation solves the linked list cycle problem using the Floyd's tortoise and hare algorithm, which employs two pointers to detect cycles efficiently. First, we define the list node class to represent each node in the linked list. Each node has a value, val, and a pointer to the next node, next. The hasCycle method takes the head of the linked list as input and determines if a cycle exists. To achieve this, we use two pointers. Slow pointer, slow, this moves one step at a time. Fast pointer, fast, this moves two steps at a time. The algorithm works as follows. 1. Both pointers are initialized to the head of the list. 2. We enter a while loop that continues as long as the fast pointer and its next pointer are not none. This ensures we don't access null references. 3. Inside the loop, both pointers are moved forward, slow advances by one step, and fast advances by two steps. 4. If at any point slow and fast meet, it means there is a cycle in the list. The return true statement confirms this. 5. If the fast pointer reaches the end of the list, i.e., fast or fast.next becomes none, the loop terminates, and the method returns false, indicating no cycle exists. This approach is highly efficient with a time complexity of O(n), where n is the number of nodes in the linked list, and a space complexity of O(1), as no additional data structures are used. This makes it an optimal solution for detecting cycles in a linked list. Here, we define the structure of a singly linked list node using the listNode class. Each node has an integer value, val, and a reference to the next node, next. The constructor initializes the value of the node and sets the next reference to null. Now, in the solution class, we implement the hasCycle method to detect if the linked list contains a cycle. This is achieved using two pointers, slow and fast, both initialized to the head of the list. The idea is simple: the slow pointer moves one step at a time, while the fast pointer moves two steps. If there is a cycle in the list, the slow and fast pointers will eventually meet. We use a while loop to iterate as long as the fast pointer and its next reference are not null. Inside the loop, we update the positions of the slow and fast pointers accordingly, and then check if they point to the same node. If they do, it confirms the presence of a cycle, and we return true. If the loop completes and the fast pointer reaches the end of the list, it means there is no cycle in the linked list. In such a case, we return false. This implementation is efficient, with a time complexity of O(n), as we traverse the list at most once, and a space complexity of O(1), since we only use two pointers. This approach is commonly referred to as Floyd's cycle detection algorithm, or the tortoise and hare algorithm, due to the way the two pointers move through the list at different speeds. To solve the problem of detecting a cycle in a linked list, we use the Floyd's cycle detection algorithm, commonly known as the slow and fast pointer approach. Let's walk through the example where the linked list contains a cycle. The input is a list with nodes 1 through 5, and node 5 points back to node 2, forming a cycle. Initially, we set 2 pointers, slow and fast, both pointing to the head of the list, which is the node with value 1. In the first iteration, the slow pointer moves 1 step forward to the node with value 2, while the fast pointer moves 2 steps forward to the node with value 3. Since slow does not equal fast, we proceed to the next iteration. In the second iteration, slow advances to the node with value 3, and fast moves 2 steps to the node with value 5. Again, slow and fast are not equal, so we continue checking further. Now, in the third iteration, the slow pointer moves 1 step to the node with value 4, while the fast pointer, moving 2 steps, reaches the node with value 3 due to the cycle in the list. Since the 2 pointers still do not meet, we continue to the fourth iteration. Here, slow advances 1 step to the node with value 5, and fast also moves 2 steps, which brings it to the node with value 5 as well. At this point, slow and fast meet, confirming the presence of a cycle in the linked list. The algorithm then terminates, and we return true as the output, indicating that a cycle is detected. Now let's consider an example where the linked list does not contain a cycle. The input is a list of nodes from 1 to 5, with the last node pointing to none, indicating the end of the list. Similar to the previous example, we initialize both slow and fast pointers at the head of the list, which is the node with value 1. In the first iteration, slow moves 1 step forward to the node with value 2, while fast moves 2 steps forward to the node with value 3. Since slow and fast are not equal, we proceed. In the second iteration, slow advances to the node with value 3, and fast moves 2 steps forward to the node with value 5. Again, slow and fast are not equal, so we continue checking. In the third iteration, the slow pointer advances to the node with value 4, but the fast pointer moves 2 steps forward and reaches the end of the list, where fast.next is none. This indicates that there is no cycle in the linked list, as the fast pointer has reached the end without meeting the slow pointer. The algorithm terminates, and we return false as the output. Additionally, for the edge case of a single node without a cycle, the input consists of just one node pointing to none. In this scenario, during initialization, both slow and fast point to the single node. On the first iteration, since fast.next is already none, the algorithm concludes that there is no cycle and returns false as the output. The time complexity of the solution is O(n), where n represents the number of nodes in the linked list. To understand why, let's analyze how the 2 pointers, slow and fast, behave. In the worst-case scenario, when a cycle exists, the fast pointer moves through the cycle at twice the speed of the slow pointer. Once both pointers are inside the cycle, their relative speed is 1 step per iteration. This is because the fast pointer moves 2 steps while the slow pointer moves 1. The maximum distance the fast pointer must travel to catch the slow pointer is equal to the length of the cycle, which is at most n. On the other hand, if no cycle exists, the fast pointer traverses the list at 2 steps per iteration until it reaches the end. Regardless of whether a cycle exists or not, the total number of iterations is proportional to the number of nodes, giving us O(n) time complexity. Analyzing the best, average, and worst cases further solidifies this result. In the best case, the list is empty or contains only one node, meaning the function terminates immediately. This results in a time complexity of O(1). For the average case, the fast pointer will traverse the list or cycle, detecting a cycle or reaching the end, which leads to O(n) complexity. In the worst case, when a cycle exists, the fast pointer must traverse the entire cycle to meet the slow pointer, and this also results in O(n). Therefore, across all realistic scenarios, best, average, and worst, the time complexity remains O(n). The space complexity of this solution, however, is O(1), making it highly efficient in terms of memory usage. This is because the function only relies on 2 pointers, slow and fast, both of which occupy a constant amount of space regardless of the size of the input. Unlike other approaches, no additional data structures are utilized, and there are no recursive calls that could add to the memory footprint. This ensures that the space required remains constant, irrespective of the number of nodes in the linked list. When comparing this approach to more naive solutions, the advantages become even clearer. A brute force method might involve storing all visited nodes in a set or hash table and checking for duplicates during traversal. While this also achieves O(n) time complexity, since each node is visited once, it uses O(n) space to store the nodes, which is significantly worse than the O(1) space complexity of the two-pointer method. Additionally, we can mathematically justify the big O analysis of this optimal solution. Each node is visited at most once by the slow pointer and at most twice by the fast pointer. Since operations at each node, such as pointer comparisons and updates, are constant, the total work done is proportional to the number of nodes. This results in O(n) time complexity. In summary, the two-pointer approach, also known as Floyd cycle detection, is optimal for detecting cycles in linked lists due to its O(n) time complexity and O(1) space complexity. It not only matches brute force methods in runtime efficiency but also surpasses them in memory efficiency, making it the preferred solution. When solving the linked list cycle problem, there are a few common mistakes to be mindful of. First, neglecting edge cases like an empty list or a single node list can lead to unexpected errors, such as null pointer exceptions or incorrect results. It's essential to explicitly handle these special cases to ensure your solution is robust. Another mistake to avoid is modifying the structure of the linked list during traversal, such as by altering the next pointers to mark nodes. This approach can corrupt the list, making it unusable for future operations. Instead, consider using auxiliary data structures like a hash set or leveraging pointer-based techniques. Additionally, improper initialization of fast and slow pointers can cause the logic to fail. For instance, if both pointers start at the head, the algorithm may not work as intended. Always ensure the fast pointer moves twice as fast as the slow pointer. Lastly, missing termination conditions in your implementation can lead to infinite loops. Always check that fast and fast.next are valid before advancing pointers to avoid such issues. Another common pitfall is using excessive memory when it's unnecessary. For example, while using a hash set to track visited nodes is a valid solution, it consumes O(n) space. A better alternative is Floyd cycle detection algorithm, which achieves the same result with only O(1) space. In interviews, it's crucial to fully understand the problem requirements. Sometimes, the question might not just ask for cycle detection but may also require finding the starting node of the cycle or determining its length. Each variation requires a slightly different approach, so clarifying the requirements is key. Interviewers may also assess your ability to weigh time and space trade-offs. While hash set-based detection is simpler to implement, it's less space efficient compared to the two-pointer technique. Additionally, edge case handling is a frequent topic of discussion, and you should be prepared to explain how your solution accounts for scenarios like an empty list, a single node list, or a list without cycles. Lastly, if you're using the fast and slow pointer approach, be sure to clearly articulate how and why the pointers eventually meet inside the cycle, as this demonstrates your understanding of the algorithm. The concepts used in solving the linked list cycle problem are applicable to several related problems. For instance, LeetCode 141 asks you to detect if a cycle exists in a linked list, which is the foundational problem we're discussing. Building on that, LeetCode 142 extends the problem by asking you to find the starting node of the cycle. Another related problem is LeetCode 287, where you need to find the duplicate number in an array. This problem uses cycle detection principles to identify the duplicate without modifying the array or using extra space. Lastly, LeetCode 202, known as the happy number problem, applies cycle detection to determine whether a number eventually reaches 1 or falls into a repeating cycle. These problems highlight how cycle detection algorithms can be adapted to various scenarios beyond linked lists. There are multiple approaches to solving the linked list cycle problem, each with its own trade-offs. The brute force method involves using a hash set to store visited nodes. This approach has a time complexity of O(n) and a space complexity of O(n). While it's straightforward to implement and easy to understand, it requires additional memory, which may not always be ideal. A more efficient method is Floyd's cycle detection algorithm, or the fast and slow pointer technique. This approach also has a time complexity of O(n), but reduces the space complexity to O(1). However, it requires a deeper understanding of how pointers move and interact within a cycle, making it slightly more challenging to implement. Another alternative is marking visited nodes by modifying the linked list itself, such as changing the next pointers. While this approach is effective with O(n) time and O(1) space complexity, it's generally not recommended. modifying the original data structure can lead to unintended side effects and is often considered unacceptable in interviews or real-world applications. Carefully evaluating these trade-offs will help you choose the most appropriate method based on constraints and requirements. Great job! To summarize, we tackled the problem of detecting cycles in a linked list using hashing techniques. This is a fundamental concept for data structures, and understanding it will help you solve similar problems more effectively. Thank you for joining, and I encourage you to keep practicing and exploring new problems. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!